Welcome to 10 by 10, Series 2. Murano number 8, The Child of the Desire. Emergence of Organic Intelligence. I only look for myself when others come. I intentionally chose to be that kind of us whether or not we bonded with them. Many Eastern and Western philosophers thought there was no distinction between matter and spirit, as we have discussed. Whitehead believed that material processes were characterized by a change in physical states, such as the movement of particles, while mental processes were characterized by the experience of subjective states, such as internal feelings or thoughts. He argued that the two types of process were interconnected and could not be understood separately from each other in the dynamic evolving process. Deleuze further believed in his difference philosophy, and focused on becoming. To him, there's no fundamental difference between material events and mind events, rather that both were part of a larger process of becoming that involved constant change and transformation of complex interplay between the two. So, he focused on understanding the ways in which different events interact and influence each other. The main flow of science and modern philosophy is not to find the fundamental matter for the mind and body, and as a philosophical chemist, I also agree with many parts. Regardless of whether a separate force or entity exists, our intelligence processes are closely accompanied by the movement of chemicals that are part of the energy flow associated with mental energy. Therefore, understanding the mysteries of the mind and body in the brain means that deep intuition can be gained by understanding the flow and combination of energy through matter. As seen earlier, transistors and logic circuits are passive beings that respond only to inputs, but in order to take on vitality, homeostasis must be achieved, as the ancestral philosophers taught us. This has been made possible by the development of artificial neural networks, ANNs, which mimic the brain with special hardware or software that controls the connections and manages circuits in software. Although the similarities between artificial neural networks, ANNs, and the way the brain processes information are impressively growing, it is important to note that there are still significant differences in the underlying mechanisms, architectures, and complexities. There are several similarities between the way a computer's artificial neural networks, ANNs, process electrical flow through transistors and logic gates, and the way the brain processes electrical charge flow through synaptic networks to create decisions and memories. Both ANNs and the brain are capable of parallel processing. In ANNs, multiple neurons in the hidden layers can process inputs simultaneously, allowing for parallel computations across the network. Similarly, in the brain, charge flow through the synaptic connections can occur in parallel across multiple areas, allowing for simultaneous processing of information. Both artificial and natural brains have the ability to adapt and learn from experience, so they have the adaptability to instantly revise and memorize many ways of connecting information with new information. ANNs use a process called training, where the weights of the connections between neurons are adjusted based on input data and desired outputs. This trains and grows the artificial brain, ANN, to learn patterns and make action decisions based on new experiences, just as natural brains do in infancy. GPT-4, which was released to the public in early 2023, learns all words, objects, or concepts with more than 2,000 high-dimensional vectors. And it transfers energy flows corresponding to 175 billion variables to express them in more than 16,000 dimensions, through the logic circuits described above. While synthesizing, then, the final decision is made through a comprehensive judgment of the hidden hierarchy, such as the evolution of the unconscious. Both ANNs and the brain are capable of nonlinear processing. ANNs use activation functions in neurons to introduce nonlinearity in their computations, allowing them to model complex relationships between inputs and outputs. Similarly, the brain's synaptic connections can exhibit nonlinear behavior, allowing for complex processing of information and decision-making that is not limited to linear relationships. Both ands and the brain exhibit a degree of fault tolerance. In ands, if a neuron or connection fails, the network can still function and provide outputs based on the remaining connections. Similarly, the brain can compensate for the loss of individual neurons or synapses by rerouting information through alternative pathways, allowing for robustness and fault tolerance in information processing. Both the an and the brain have the ability to create memories and create homeostasis. In ands, memories are stored as learned weights in the connections between neurons, allowing for recall of previously learned information. Similarly, in the brain, memories are believed to be formed through changes in synaptic strength and distributed across various regions, allowing for recall and retrieval of past experiences. There are bound to be similarities between the hidden layers of artificial brains and the networks of neurons, or interconnected areas, in the natural brain that process information and generate responses. Through these areas of natural brain, they process and integrate information from various inputs to generate outputs, which could be behaviors, perceptions, or cognitive processes. For example, in visual processing, there are multiple layers of interconnected neurons in the visual cortex of the brain that process visual information from the eyes and generate representations of visual stimuli. These interconnected layers of neurons synthesize visual functions at varying levels of complexity, with aggregated and diversified information ranging from basic functions such as edge and orientation to more complex functions such as object recognition. The analogy between hidden layers of ands and the brain is not perfect and should be taken as a rough comparison to help understand the concept of information processing in the brain. The brain's functioning is still not fully understood, and ongoing research is continually expanding our understanding of its complexities. The evolution of the brain is a fascinating journey spanning billions of years of life on Earth, and we believe it will help us understand artificial intelligence synthesis. It is believed that the brain has evolved gradually from simple sensory organs in primitive life forms to the complex and sophisticated organ that it is in modern organisms, including humans. The earliest forms of life on Earth were single-celled organisms, such as bacteria. These primitive creatures had basic electrical sensory abilities, such as sensing light, temperature, and chemicals in their environment, which helped them survive and react to their surroundings, like turning a motor on or off with the flick of a switch. Over time, the neural roles of organisms become more complex, as their ability to aggregate and weight information to gather information from their environment has become a survival advantage. For example, some early multicellular organisms developed simple light-sensitive cells, or photoreceptors, which allowed them to detect and respond to light. These photoreceptors become more specialized through mutation and form a cluster, which is advantageous for knowing the distance to the enemy and sustains the electrical signal to remember the opponent. As life forms continued to diversify, their sensory information flow as electric flow became more connected, elaborate and specialized. The primitive nervous system is made up of clusters of nerve cells that help coordinate basic sensory responses, and furthermore, as we saw, ganglia that synthesize them to make decisions, resulting in increased brain size and segmentation, complex stratification of subdivision, and increased survival rates. As diversification progressed, the nervous system became more complex and centralized, leading to the development of a true brain. The brain, the control center of the nervous system, has departments that connect and control different areas at a higher level that are responsible for various functions such as sensory processing, motor coordination, and higher cognitive functions. At the heart of natural brain function are our next topic, proteins. Thank you for watching.